Hi everyone, today we're going to graph logarithmic functions and find key characteristics from the graph, like domain and range and your asymptotes. We'll also learn how to use the change of base formula to evaluate logs on our calculators. Let's get ready to unlock the power of math together. Let's dive right in. So it's important to understand what our change of base formula is. Now, this can be mandatory for some calculators, depending on which one you have. And it's also going to be helpful for everybody to be able to understand what this formula is. Now, the change of base formula is just being able to rewrite our logarithm with different bases. Now, what we're doing is we're taking our logs, and we have a log in the numerator and a log in the denominator. And then if we happen to have a base of b, we are just rewriting this logarithm with a base of b. Now, our argument, which is right here, which is in this case x, is going to go in the numerator, and then our base, which is a, is going to go in the denominator. Now, you can rewrite this no matter what sort of base you have. So you could have a base of 10, which we know is our common log, which we know it's not required to write the base of 10, but you can if you'd like. But still, again, our argument is in the numerator and the base is in the denominator. Now, again, you can write with a base of e, but remember that the log base e, let's say of x, is the same thing as our natural log. So we can have ln, and again, our numerator will have our argument and the denominator will have our base. So log base e is the same thing as our natural log. Now, there are some calculators, if you have a TI-84CE or a TI-84 Plus, that you actually have an option to do this in what's called your log base option. So that means you're going to go to math, and then you would choose option A, and that is log base. And what that does is it pretty much gives you your log, gives you a little box, sort of as a subscript for the base, and then you can put some thing, whatever it's a variable or a variable and a number, you can put that in the spot for your argument. So if you wanted to graph a logarithm and you were not able to use the log base in your calculator, like you don't have that option, what you're going to do is just use your change of base formula. So you would type in log of your argument, which in this case is x plus 3. You would divide, and then you would take log of your base, which is 2. Now, in the second option, in order to rewrite, you would do log. Now, be mindful of what is exactly your argument. Your argument is only the x because you don't have parentheses. And then you would divide by the log of your base, which is 2. And then you would take the plus 3 and you would add it at the end. So again, if you don't have this log base option, you would have to use your change of base formula. Now, even if you have log base, you might see problems that do not have any numbers and they're just variables everywhere. So now what we're going to do is give you an example so you can check to see how you would choose this expression that is equivalent to log base g of w. Now keep in mind, again, what's your argument? That's w. So we know that the argument is going to be in the numerator. So we're going to look and see which ones have w in the numerator. Here, here, and here. And then our base is g. So remember, the base has to go in the denominator. Now we're going to look, see where we have g in the denominator. Again, 3 options. So what we have is we have 3 expressions that are equivalent to log base g of w. Now notice that the bases are all the same, right? And that's okay because if your bases are all the same, right, we're able to do our change of base formula. As long as the bases are the same, we can rewrite our logs. Now here we're going to look at the properties of logarithmic functions. Now just remember that log functions are inverses of exponential functions. And if you need to review exponential, you could check out the video linked above. Now, with these being inverses, some things to remember is that certain characteristics are going to be reverse or inverse, right, of what exponential functions are. So with exponential functions, our domain was all real numbers. Now with logarithmic functions, our range is all real numbers. Now our asymptote for exponential functions was horizontal asymptote at y equals 0. Now inverse has a vertical asymptote at x equals 0. So right on that y-axis here. Now, with your vertical asymptotes, some things to remember is that those vertical asymptotes are going to be affected by horizontal shifts now. Okay, horizontal shifts, because we're going to go either left or right, and that's going to move that vertical asymptote. Now, again, that domain is going to be affected by any shifts or any reflection. So just keep those in mind. Okay, so now what we're going to do is we're going to use a calculator and we're going to graph our functions and identify key characteristics. Now, something for you to be aware of is what your argument is. Now, our argument here is this x plus 3, so be mindful of that parenthesis. All right, so here we're going to go to y equals, and again, if you have the log base option, you will go to math and go to log base. So our base is 2. Our argument is x plus 3. And remember to go out of the exponent to type in that minus 4. Okay. If you don't have the log base option, what you would do is you would change a base formula. So you would do a log, and you would do your argument x plus 3 parentheses. And you would divide by the log of 2. That's your base. Close it, and then type in that minus 4. Okay, so here we have our graph. Okay, now remember where your vertical asymptote is. You do have a horizontal shift to the left 3, and then you'll notice that your graph sort of shifts to the left. Okay, now the asymptote is that x is equal to negative 3. That does impact your domain. Now, in order to find my y-intercept, that is from our table, so second graph. And here, when x is 0, there's my y-intercept, so negative 2.415. Now, to find our x-intercept is where my y is 0. So let's see if we do have a nice number for our x-intercept. Oh, it is here. So we will have an x-intercept at 13 and 0. So now that we found our information, again, let's graph. So our asymptote is x is equal to negative 3. We do have some points that we can put in there. So that was negative 2.415. And then our x-intercept was at 13, a little bit off our graph, but we can find some other points. You could go to your table again and just approximate some points here. And I'm just going to put some points for the sake of the problem. Okay, so again, remember, does not stop even though your graph in your calculators may appear to cut off. We do have your graph continuing in both directions. So my domain, right, my asymptote negative 3 going to infinity, and range is all real numbers. Now what we're doing for our increasing or decreasing is we're looking at our graph here, and we are saying my function is increasing. Now it is increasing on the domain of negative 3 to infinity. And then we're also going to look at end behavior. Now, when we look at end behavior, we're looking at what our function is doing as we approach to a certain number, right? So when we look at our end behavior, we're going to look as x approaches some number and as x approaches some number, like what is my function doing? So as x approaches, 3 because we have 3 over here, right? That's where we sort of stop our asymptote. As x approaches 3, and then we're going to put this little plus sign. Now, what that plus sign means is that as x approaches 3 from the right side, right? So as x approaches 3 from the right side, okay, what is my function doing? So my function, or my p of x, or my y values, they are approaching negative infinity. Now, as x approaches, we're going to look from the right side, right? So what's happening over here as I go in this direction, right? So as x approaches, those x's are positive infinity. My function, or my p of x, approaches or points towards the positive infinity numbers for my y values. Now, end behavior does sort of give you a little bit of an introduction when we get into our limits unit. So now let's go ahead and look at a second problem together. Okay, so here you have your natural log. Okay, now still ln, still in your calculator. Please keep in mind that because we have a +2 inside your function, right, inside that parentheses, you are going to be moving that asymptote to the left. So we right away will know that my asymptote is going to be at -2. All right, so let's go ahead and graph. Okay, so here, let's go back to y equals. We're going to go negative, so that's the negative button that's below the 3. ln, right below your log, or to the left of the 4. And you have x plus 2, close your parenthesis, and then -1. Now if we go ahead and graph, now when you look at this graph, it does look like it stops, but it doesn't. In actuality, it gets very, very close to that asymptote that's there at x is equal to -2. So just be mindful on how you draw. You do need to continue that graph running very close to your asymptote. So let's go ahead and find our y-intercept from our table. So second graph, let's go to where x is 0. And we have -1.693. That's my y-intercept. And my x-intercept, I don't see that we have our error, right, where our asymptote starts. I don't see we have an x-intercept. That's a whole number, but it's clear from our graph that we do have one. So 2 ways you can find an x-intercept. The first way would be second trace and then go to 0. And then right where the x-intercept is, we're going to go a little bit to the left. So click that left button. It looks like it goes above. And a little bit to the right of that intercept. So it looks like it goes below your graph. Enter, enter. So then your 0, or your x-intercept, is -1.632. Now another way you can do this is in your y2, we're going to put 0. Y equals 0 is the same thing as your x-axis. Now you can find the intersection. So we're finding the intersection of our x-axis with our log function. So second trace, and you're going to go down to intersect, move a little closer to your x-intercept, and enter 3 times. And then same x-intercept of -1.632. So we have -1.632. And my y-intercept of -1.693. And we have another point that was approximately from our table. What was that? 3 and a little bit more than -2 here. So from there, again, looks like it cuts off that graph, but you do continue with arrows on both sides. So our domain, asymptote -2, comma infinity, range -infinity to positive infinity. So let's look at our graph. What's it doing? Our graph is decreasing on the domain of -2 to infinity. And end behavior again, right? As x approaches some number, and as x approaches some number, what's my function doing, right? So we're looking at sort of that end of the domain, which is -2. Right, so at -2, I'm going this way, right? What is my graph doing? As x approaches -2 from the right-hand side. My function, or m of x, or my y values, are pointing towards positive infinity. Now, as x approaches, what's going on this way? As x approaches our positive infinity, those positive infinity numbers, x's, positive x's, my function, m of x, is approaching negative infinity. Thanks for learning with me today, unlocking the power of math one problem at a time. Don't forget to like and subscribe for future notifications on pre-calc videos. See you in the next lesson.